First thing we need to know are some of the words that we're going to be using. So for our x variable, what you're generally going to see in statistics is that the x variable is called the explanatory variable, and that the y is called the response variable. So in general, when we're doing a study or an experiment, what we're going to do is we're going to choose the x values, the times, the masses, whatever it is that we want to measure, or how often we're going to measure it. And then the y variable is what we're actually going to measure and see what happens to it at each of those x values. So that's why it's called the response variable. In other places in math, I'm sure that you've heard the x variable as the independent variable and the y variable as the dependent variable. That is still true, but we just give them these extra names in statistics. In Chapter 9, what we're going to be looking at are some scatter plots to determine whether or not our variables have any sort of linear relationship between them. There are lots of other relationships in math, but at this level of statistics, we're just going to be looking at whether or not the data seems to be related in some sort of linear fashion. So what we tend to say is that if the scatter plot does not resemble a line very much, then what we say is that there is no linear correlation. Oops, I forgot the no. No linear correlation. That doesn't mean there's no relationship between the x and y variables. There's just not a linear relationship that's very evident from the variables. Okay, so if we are looking at a scatter plot like this, then we can clearly see that when we say linear, we mean straight line. So if the data resemble any sort of straight line, we call it a linear correlation. You can see that this data does not have if I were going to draw a picture of what this data looks like, I'd probably go like that. It kind of looks like a happy face. So this data does not resemble a straight line. It resembles a happy face, so that's no linear correlation. Over here, these dots are just everywhere. This has no shape or pattern to it whatsoever. So that's why both of these are said to have no linear correlation. Okay, so if you have a scatter plot and the points seem to be in a straight line, but they are not exactly all on the same line, then what we say is that they may have a low or moderate linear correlation, depending on how close the points are to fitting on a line. Okay, so for example, if I have a graph and I have some dots and they kind of look like this, okay, I could say, okay, well, those, it kind of looks like my data kind of looks like that. They're kind of going in that direction. That would be a low or a moderate linear correlation. What I like to think of it is if I could take a kind of a fat highlighter and I go through those points and I can collect the points by doing that, then that's a low to moderate linear correlation. The skinnier the highlighter that I can use and still collect all the points, the higher the linear correlation between those points. So if all of the points are on the same line, exactly the same line, then we call that a perfect linear correlation. And as you can imagine, that's not really the most common thing to have happen with a set of data. Okay, so again, if I have a point, point, okay, and this is my data that I've collected from my study, then you can see those line points, all those data points lie on exactly the same line. That is a perfect linear correlation. Now, in statistics, if something has a positive slope, then we say that that has a positive linear correlation. And if something has a negative slope, then we call that a negative linear correlation. So let's take a look at these diagrams down here, and you can see that they're labeled for you to match the notes that we just took up there. So again, A and B have a low to moderate linear correlation, but C and D have a perfect linear correlation because every dot lies on exactly the same line. So take a look at example 2. I'll give you a minute. See if you can figure out how to match up the ABC diagrams with the ABC. Go ahead and pause your video, and then we'll answer the question. Okay, so what did you decide? Which of these diagrams has no linear correlation? Well, it's going to be diagram C. Diagram C to me kind of looks like a king cobra or something. Definitely not a straight line. B, which one has a perfect linear correlation? I'm going to match that up with A, because again, if I get out my ruler, I can see that all of those lie on the same line. And C, which could be reasonably, it kind of looks line-ish, but I can't do it with my pen. I have to get out my highlighter, and now with my highlighter, I can say, it kind of looks like that. Okay, so hopefully that's pretty straightforward. Just being able to identify a linear correlation. Okay, moving on to something a little more interesting. We need to be able to create a scatter plot. So you should have been creating scatter plots for a very long time now. A scatter plot is nothing but plotting XY points on a graph, correctly labeling your X and Y axis. So what you're going to do is you are going to go ahead and you are going to look at your X numbers and your Y numbers. You're going to decide what you need to count by. Your Y count, how you count on your Y-axis, does not have to be the same way that you count on your X-axis. It can if it's convenient, but it doesn't have to be. You need to make sure they're labeled and counted in the correct manner. So go ahead and pause your video, label your X and Y axis, and then we'll get started with our graphing. Okay, so I've got my axes labeled. Almost. I forgot to label my Y-axis. What does my Y-axis tell me? Hours in safety training. Okay. So now we should be able to, once we've got it correctly labeled, we're going to go ahead and graph our XY points and make a scatter plot. So please go ahead and graph each of the XY points. Okay, so there we go. I have plotted each of my XY points, 10, 80, 19.5, 65, 30, 68, etc., all the way down to 80, 12. Once I have a scatter plot does not get connected dot to dot style. Okay, it's just a scatter plot, points on a graph. Okay, so A was make a scatter plot. B, as the number of hours spent on training increases, okay, so as my X gets bigger, what happens to the number of hours lost due to accidents? So what's happening? As x goes this way, what's happening to the y numbers? Okay, right. The hours lost to accident decrease. Okay, so in math, what do we call that? They are inversely proportional. Okay, what type of correlation does it have? Okay, so my choices are positive linear or negative linear, and then strong, moderate, or low. Okay, so let's start with positive or negative. That's the easier one. So it has a negative. It does look line-ish. It's not a perfect line, but it is line-ish trending in this direction. And what do you want to call that? I would agree with either moderate or low. I'm going to say moderate. Definitely not high. It's not really a great line. Linear correlation. Oh, I can't write off the paper. Okay. D. Remember, this is something that we used to do back in Algebra 1, where you've got the scatter plot, and then they want you to sketch in what you think looks like a good guess as to the linear trend of this graph. So again, go ahead and get a different color. And I'm going to say, you know, if you have a ruler or the edge of your calculator, you can lay it down. I don't have that because I'm writing on my computer. But I'm going to say it looks something like that. That's kind of the trend that we're seeing with this graph. Maybe not perfect. Maybe I wanted to slant it a little bit more. But again, it is linear-ish, and that's all I need to show. So in order to more precisely define how much of a correlation there is between the x and y variables, how related they are in a linear fashion, in statistics we use something that's called a linear correlation coefficient. And so the first thing you have to know about the linear correlation coefficient is that it's called R, and R has no units. Okay? It's essentially describes the percent of a linear relationship. It is always somewhere between 1 and -1. It can equal 1, it can equal -1, but it cannot be any numbers bigger than 1 or smaller than -1. If R is greater than 0, that means it's positive, right? Okay, that's going to give us a positive correlation. If R is less than 0 means negative, so that's going to give us a negative relationship. And if our R equals 0, that means that there is no linear relationship. Okay? Now, the really interesting thing about this, kind of surprising actually, if you think about it, is most of the time, if you switch your x and y values, you'll get a completely different answer to the question. But if you switch around your choice for x and your choice for y and actually use them backwards, it does not change the value of R. It's a very unusual result because what it's describing is the relationship between the two. So it doesn't matter whether x is first and y is second, or y is first and x is second. The amount that the two are related, which is what R measures, is going to be the same. Okay, the other thing that's very interesting is that changing the units of the variables does not change the value for R. Okay, so if we're both measuring the length of something, and one of you measures it in meters and does all of your work in meters, and somebody else does all of their work in feet, your value for R will come out the same, because again, R is describing the relationship between the variables and has nothing to do with the units that it's being measured in.